Hello again. This is the lecture for week 7. Today we're going to be going over ANOVA. It's going to really build on last week's, but this time we're going to be talking about repeated measures ANOVA and then mixed ANOVA. Repeated measures is just like the paired samples t-test, but it can handle more than 2 time points. And mixed ANOVA is going to combine repeated measures ANOVA and one-way ANOVA together into one. So just a reminder, this is generally how you can think about things. I don't have mixed ANOVA on here, but it's just a combination of 2 of them. So repeated measures ANOVA, it's when we have repeated measures, 2 or more, usually 3 or more we start to use this. 2 or more, or just 2, we generally just use a t-test. So you can think of it as time 1, 2, and 3, where we have the same people at each time point. And we measure the same dependent variable at each time point. So we have this guy, this person, all the way down, and they're in every time point. But actually how ANOVA works is it's going to be working with difference scores, just like the paired samples t-test. ANOVA, repeated measures ANOVA, uses the difference scores, but now instead of just one difference score that we had in the t-test, we now can have 2 or more. So difference score 1 would be time 2 minus time 1. And then difference score 2 would be time 3 minus time 2. So now we have a couple different scores that we're working with. So some general requirements: we need a dependent variable on an interval or ratio scale measured at 2 or more time points. And the other requirement is the participants need to be present at each time point. If they miss one time point, they're dropped from the analysis. And that's because we won't have a difference score for them if they're missing any of the time points. So of course we're going to use the same 6-step approach. First one, this is the first time we're going to introduce what's called sphericity. It's a fun word. It just means that different scores must have equal variances. They're very similar to what we've done with homogeneity of variance. But like with the t-test, the paired samples t-test, we're going to be working with the different scores. So first thing, individuals are independent of each other. The appropriate measurement, we need an interval ratio dependent variable. We want normality of the residuals. We use a QQ plot again. And then sphericity. The variances of the different scores should be roughly equal. To examine these, we want a random sample. We got to know what our variables are. We can look at a QQ plot, and then sphericity, we're going to use what's called the Mauchly's test. We'll talk about that more in class. We'll show an example, but it just tests, just like Levine's, it's going to test for that assumption. Step 2 is stating the Null and Research Hypotheses. This is going to be very similar to what we've done with ANOVA before, but now we're talking about time points instead of groups. So the research hypothesis is that at least one time point, the mean of the time point, is different than the others, where the null is that all are the same. So verbally, the research is one of the time points means is different than the others, at least one of them. And then the null is that there is no real difference between the time points. It's just random chance or sampling error. So we're going to, of course, define our critical regions, essentially answering this question: how much evidence is enough to believe the null is not true? So before analyzing the data, we need to define the critical region, and generally we're going to go with the alpha of 0.05. Here we decide on the alpha first, and then we're going to compare the p-values in step 4 to our alpha level. And again, with ANOVA, we have 2 different degrees of freedom. The first one is k minus 1, where k is a number of time points. So if we have 3 time points, then our df numerator is going to be 2. And then our df denominator is n minus k, where n is our total sample size. The next step is computing the test statistic. So this is output from Jamovi. Right here, we have the line that is most important for us to analyze. This line and this line are just different versions of the residual. But this line is going to tell us if at least one of the time points is different from the others. And here we get a p-value that's really small, so we're saying, yes, it looks like the mean of one of the time points at least is different than another time point. And then we also have our effect size, which is the eta squared that we talked about before. So here, 0.116, that's telling us that the time variable, so in this case of productivity, the time of it, accounts for 12% roughly of the variance in all of productivity. So time accounts for a lot of the variability in the outcome. Data could look like this when we're using a repeated measures ANOVA, where each line is a single person measured at, in this case, 3 time points. What we want to know is, are people changing from different time points? And here we have this person, they go up a little bit and then up a little bit more. There's 2 people here, they go up a lot and then just a little bit. This person actually goes down and then up. So what we're trying to do is pick out patterns and try to understand, on average, where is the change happening over time. So the F statistic and p-value tell you if one of the times is different than the others. But it doesn't tell you which ones are different if you have 3 or more time points. So again, we could use post hoc tests to understand where the differences are over time. Just like before, post hoc usually refers to comparing all the groups or times, where contrast is just comparing some. And then again, we're going to have our eta squared. It is how much of the variability time accounts for, divided by all the variability. We're going to have the same cutoffs we did before with eta squared. And then step 6 is putting your results into words. We'll have a few examples of this in the in-person class. Alright, so that gives you kind of a heads up of what repeated measures ANOVA looks like. It's a lot like the paired samples t-test, but it can handle more time points. It's also a lot like the one-way ANOVA, where you're actually using time instead of independent groups. I'm going to talk about the differences and similarities between repeated measures versus mixed ANOVA, because we're going to introduce mixed. We're not going to get into a ton of detail, but I want you to know what it looks like. So repeated measures ANOVA has one time variable. It tests for any differences across the times on the time variable. So we're just going to go from time 1 to 2, is there any difference there? And time 2 to time 3, is there any difference there? Repeated measures ANOVA can also have multiple repeated measures. We're not going to give an example in this class, but it is possible to have like a 2-way repeated measures ANOVA, just so you're aware. On the other hand, there's what's called the mixed ANOVA. Mixed ANOVA combines one-way ANOVA and repeated measures ANOVA. And it tests for any differences across the times and groups at the same time and their combinations, which is the interaction that we talked about before. So an interaction in mixed ANOVA could look something like this. We have a treatment and control group, and we measure both of them across time 1, 2, and 3. Our control, it looks like, roughly stays the same, maybe drops a little bit. Where our treatment, it looks like over time, overall, there's increases. This would be an interaction between time and group, where the effective time depends on what group they're in. The effective time for control is negative or flat, and the effective time for treatment is positive, so it's different depending on what group they're in. That is a mixed ANOVA interaction. This is a really common design in experimental research where you want to look at does the effect of time, so maybe we're given an intervention of some sort, and so control, we're just either given a placebo or treatment as is, and then treatment, we're giving them this new intervention, and what we're hoping for is that there will be an interaction between time and group, because that would tell us that the effect over time, the change over time, depends on what group you're in, and so maybe our treatment is actually working compared to placebo or control. This is a mixed ANOVA output from Jamovi. You have the two tables again, but this time this table actually includes more than just the residual. Now it has the group variable, and that tells us something about are there differences across the groups. And then the within subjects effects, it has the time like we had before, but now it has time by group. So this is the interaction right here. So we have three things again, just like we had in the two-way ANOVA, but this time the interaction is between the change over time and the group. When we do that, in this case, we have time by group, and it is significant. So it's less than 0.05, so we do have an interaction. The effect size is a little bit bigger than small in both of these measures. This is the generalized and just the regular. They'll usually be pretty similar. In this case, we don't need to really concern ourselves with the main effects of time or group because we have an interaction. And what we'd be talking about is what that interaction means. And one way we could find that out is looking at a plot like this. And so if this was our situation where we have group where it's control or treatment, and we have time, and our interaction is significant, we would come here, do a figure and say, well, it looks like treatment has a positive effect on the outcome over time, where those in the control group either don't change or they decrease slightly. And so that would be part of our interpretation. So generally we don't just interpret this on its own. We'll want to say, what does that mean here in this situation? And usually a figure is really helpful there. So if the interaction wasn't significant, one thing we could do is just remove it from the model. I'll show how to do that in Jamovi. And then we could just interpret time and group on its own, the main effects. So the whole idea is ANOVA, in all the ways that we've talked about it, is very similar. When we had one-way ANOVA, we're just comparing two or more groups. When we had two-way ANOVA, we're comparing two or more groups across two different variables. And as such, we can look at their interaction, see how one depends on the other. With repeated measures ANOVA, now we're looking at change over time. And then mixed ANOVA just combines one-way ANOVA and repeated measures ANOVA, where we can look at change over time, and we can see if that change over time depends on what group you're in. So if you do have questions, please post them to the discussion board before class starts, so we can make sure we answer those. In class, we'll definitely show how to interpret these. We'll show how to do them and then the interpretation of them. And then, like I mentioned before, the week after we'll have more review, so this will be the last pre-recording for the ANOVA information. When we come back, we'll have information about correlation and regression next.